So today's video we'll be talking about quantum mechanics, and in quantum mechanics we'll talk about superconductors. Superconductors. Superconductors are low temperature, very low temperature, very low temperature, resistance free means at low temperature what happens is that their resistance decreases to a certain point that they start levitating. In okay, such a way that they will they will experience some kind of repulsion. Okay, and there is the amount of temperature required is 4 Kelvin, 4 Kelvin more than the required, more than the absolute zero, which is 169 degrees Celsius. Okay, oh sorry, 169. So what happens is that over here, when it reaches this decrease is done for a helium gas, for helium, not gas, for helium. Okay, and when the resistance decreases, the electrons flowing in that metal, the metal which we use, the electrons flowing inside them are arranged in such a way that they will not disturb the lattice, and they will move as a pair. They will move as a pair, and we will talk about that later on. Okay, but before that, let's talk about how this lattice, because what is resistance? First of all, resistance is like when we have a metal. Okay, and we have a metal, let's suppose any metal, and the outermost electron of that metal is a dislocalized, delocalized, not dislocalized, delocalized electron. Okay, so what happens is that that electron, wait, let me just increase this, that electron, not that much, when that electron, then when we pass electricity through that metal wire, or that metal, what happens that because of the free electron, when we give additional electrons to the wire, to that metal, what happens is that when electron is passing through, these proton these lattice, they will have charges, and they will get attracted to the electron, and then we will have cases when electron will bump into the lattice, will into these um, atoms, whatever. Yeah, so when they are bumped, okay, what happens is that they will absorb energy. Okay, they will absorb energy, and that is what energy loss. Now now we have a loss of energy, right? Energy loss, it can be heat, because if you like, let's suppose we have a adapter. Okay, for when we put it into the socket of the socket, what happens is that if you keep your finger or your hand on top of that socket, you will start feeling you will feel the heat, and that heat is nothing but energy loss. So what superconductors are, that they are, for them for them energy loss is not even existing. In superconductors there is no energy loss, but that's only possible when at low temperature. How? Because let's suppose we have a metal plate, on that we put a superconductor. Okay, what happens is that if the metal um, starts to, at first when it has a certain temperature, the what do you call that, the magnetic field, it will go it will go through the wire, the metal. What? The magnetic field. Magnet mag sorry magnetic field. Okay, so what we want, so this is the case, but if you have the same metal with a conductor on it, a conductor, and we increase the temperature to 169 degrees Celsius, what you will see is that the conductor rises and the field doesn't go through the metal. At first it was go through, okay, but then doesn't go through. Okay, so that's the property of a superconductor, that at low temperature energy loss is reduced so to a certain point that superconductors start levitating. And so first let's talk about how we could we could make like such type of superconductors. So how it's done. Okay, so how it's done is that we know that there are two types of elements, fermions, sorry, two types of particles, fermions fermions and bosons. Okay, fermions have half integer spin. Okay, plus minus half integer spin and half spin, whereas on the other hand bosons have integer spins. Okay, they have integer spin. So the property of fermions is that they can exist on the same energy level in a group. They like to be on that level. They like to be on that level. That's the quantum explanation. For superconductors to understand superconductors, we have to talk about quantum mechanics. This is where quantum mechanics jumps in. So on the other hand, bosons, their property is that they only like two of them on each level, that they cannot take in more or less. Okay, they're fixed amount. These are the fixed amounts such that they are opposite. They have opposite. I think spin, or was it spin or charge? Spin. Okay, so then after that, so yeah, when we talk about the conductors, what conductors actually have is, when they're not decreased to so low temperature. They're not decreased to low temperature. They act as fermions. They go here, here, bump into this, and lose energy. That energy is but nothing but the heat energy which we feel when we touch them. We touch the conductors. The not the conductors. The whatever that instrument or circuit is. So what we do is that when these and these over here pairs, they are known as Cooper pair. Cooper pair. Okay. So when we decrease it to the certain temperature, these electron they will turn into Cooper pair. They will become one. And at this point, at this point, what you will see is that these have integer spin. Integer spin. Okay, they have integer spin at this point, so they become Cooper pairs. So that's the reason that the what happens that that's the reason they start to act as certain in a such a way that now these lattice which were moving up and down again and again now are at the fixed point and they act as one entity. And again, them acting as one entity is one more something known as Bose Einstein condensate. Condensate. What is Bose Einstein condensate is that when we decrease the temperature of a um, certain particle or a group or lattice, their wave function or their waves, let's suppose how I say is that Bose Einstein Bose Bose Einstein condensate condensate. Okay, so when separate they look like this. The wave functions look like this. Each have this separate wave functions in that lattice. But when temperature temperature is decreased, okay, not when I say decrease, it doesn't mean low, like less. Not the change is not that much. It's a lot. The change is a lot. Change in temperatures, a lot. Change in temperatures, a lot. Okay. So what happens is that wave function change into into one entity one entity sorry entity. Okay, and they will turn into like this. That means what we show is that now at this point they have one property. They all have similar property, one property. Over here, when we talk about the particles, that when we try to stop the particles or to make sure that they have exactly one position, here there is a phenomena known as not phenomena principle known as Heisenberg's principle, which states that you cannot have a definite position or momentum as per this equation, which is this. Okay, this Heisenberg's uncertainty principle. Sorry. So what happens next is that, okay, yeah, so this is a wave function, how they exist. Then moving back to the topic, the one we were talking over here, what we said is that now, since they have they're one entity, every single point they will have a negative charge. If they're here, they will have negative charge. If they're here, they will have negative charge, such that because they have their electrons which are moving through, so they will be, this pair will be negative charge, they will act as one. So that's how superconductors are do work. As first they have half spin, and they get interacted, the energy is lost. But when we decrease the temperature to a certain point, such that their movement is decreased to a certain value, it doesn't decrease to zero, there will be some resistance. It's very, very, very less. Okay, note that the preciseness will not be 100%. There will be some preciseness which is low, but that, what we say is that resistivity, if I make the graph, if I make graph, we say that this is R and this is temperature. If I'm right, that's how they are. When we increase the temperature, resistivity no, decreases. Wait, it should be opposite. Temp and resistivity. Oh no, it's opposite. Okay, so what happens is that when temperature uh, is less, resistivity is also less in terms of, it's in negatives to positive. So this is how it will go, and then come down again. So here one more thing is that up to certain temperature, resistivity resistivity will will rise will rise, then fall again. Okay, okay, so no, sorry, it's opposite. Rise and fall, rise, then fall again. Okay, so what we do is that, this is just one example, key point. So energy level is decreased over here. This is known as valence. Okay, this is known as valence. So what key point here is that, so then when electrons, over here to give the example of fermions and bosons, what we say is that fermions can be electrons and bosons are um, photons, we can say. So superconductors, they have the list of superconductors, that what we could use as superconductors are Al, Bi, then Cd, and these are symbols. And Kd, cadmium, 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 something like that. And then aluminium can also be one of the superconductors. And the best thing about superconductors is that they the levitation, if we do the practical, the best thing is the levitation, that the magnetic field will not go through the metal, but now that it will the that superconductor will rise so that magnetic field can go again back to its position. Okay, so one more thing, when we talked about the spin of the particles, the spin, the word spin doesn't mean actual spin, it's just the representation, normal or simple representation of such a way that they spin while they're not spinning, such that they are like some dots which orientate in such a way that they again come back to their original position. That's what spin is. Okay, spin. Okay, what is spin? Orientation such that they they are point like particles which want the not want which take some certain number of vector changes to return return to its actual uh, shape. Okay, just like example, if we have like this thing, so for it to return to its actual shape, it would have to orientate or spin two times. Okay, that's how it would be. And then where else, what else could we say? Yeah, that's it. So again, what we the Bose-Einstein condensate is the main important thing, that we decrease the temperature such that they start to act as one entity, and the vibration or the up and down of the lattice stops to a certain point, that they are not the electrons in pair, Cooper pair, can simply go through, and that is superconductivity. There is no resistance, and there is no resistance for the magnetic field to stop.